Welcome to today's session in physics. Today we are discussing force acting on a current carrying conductor in a uniform magnetic field. In this experimental arrangement, we have a horseshoe magnet, and between the pole pieces of a horseshoe magnet, we have a bare copper wire which is connected with the help of insulated copper wire. Now, when the key is inserted, current flows from the battery and the circuit is closed. You can see the bulb also is glowing, and we can see that the bare copper wire, it deflects from its position. When the key is taken out, there is no deflection. Now we can change the direction of current by changing the connection on the battery. So in that way, the direction of current through the circuit, it is reversed. In that condition, when we insert the key, it is found that the bare copper wire, it shows a deflection in the opposite direction. But it shows the deflection. When the key is taken out permanently, there is no deflection for the bare copper wire, which means that the bare copper wire, it is under the action of a force only when a current is flowing through it. Or in short, a current carrying conductor experiences a force in the presence of a magnetic field. Now consider a current carrying conductor of area of cross section A and length L placed in a uniform magnetic field. Let N be the number of free electrons per unit volume of the conductor. So as we know, when a current carrying conductor is placed in a magnetic field, in the current carrying conductor, all the free electrons, they are under a process called drift. So due to this drift, all the electrons, they have an average velocity. That's what we call as the drift velocity. So it is similar to a situation when a group of charges are kept in a uniform magnetic field. So all these electrons will be experiencing a force which is equivalent to the Lorentz force. Since all the electrons have the drift velocity in the same direction, all the electrons will be experiencing this Lorentz force in the same direction. So collectively, the conductor as such experiences a force. And now the direction of the drift velocity and the direction of magnetic field, they are perpendicular to each other, because drift velocity, it is in a direction opposite to the direction of electric field. So this drift velocity and the magnetic field, they are perpendicular to each other. So the direction of the net force can be easily found using Fleming's left hand rule. So now coming to the expression for force experienced by the conductor, we have total number of electrons in the conductor as volume into N, where volume is area into length. So we have the total number of electrons as ALN. Therefore, the total charge becomes ALNE, where E is the charge of an electron. Therefore, the force on the conductor is given by Q Vd cross B, where Vd is the drift velocity. So, substituting for Q, we have F is equal to ALNE into Vd cross B. Now, in the next step, we are rearranging that equation, taking Vd out of the bracket and L into the bracket. So when we take L into the bracket, that L has to be made a vector. So in the next step, NeAVD is substituted as I. So we have I into L cross B. So here, what is this L vector? Actually, IL is together taken as vector. IL is together taken as vector, and it is called as current element. This is because of the problem that current is already defined as a scalar quantity. So to attach that vector nature, we define IL as a vector quantity, and IL has the direction the same as that of the current. So IL is called as what? Current element. So the expression for force experienced by a current carrying conductor whose length is L and the current passing through it I, then the expression for force is given by IL cross B, where L is the length and B is the magnetic field. When the magnetic field B and the current carrying wire of length L are perpendicular to each other, the force on the wire is given by F is equal to BIL, and this force is the maximum force experienced by the wire, and its magnitude is given by BIL. And in such situations, that means when the directions of current and when the magnetic field are perpendicular to each other, the direction of force can be found easily by Fleming's left-hand rule. So by Fleming's left-hand rule, you can take the three fingers of left hand in the three mutually perpendicular directions, and if the thumb shows, that means if the index finger or the forefinger shows the direction of magnetic field and middle finger shows the direction of current, then thumb will be showing the direction of force. And take care, they are to be held in three mutually perpendicular directions. Now we'll discuss a problem. A conductor in the form of a right angle ABC with AB equal to 3 cm and BC equal to 4 cm carries a current of 10 ampere. There is a uniform magnetic field of 5 Tesla perpendicular to the plane of the conductor. The force on the conductor will be, so this is perpendicular, it's given. So F is equal to BIL. So substituting, we will get 2.5 Newton. Next one, a wire of length 50 cm and mass 10 gram is suspended in a horizontal plane by a pair of flexible leads. The wire is then subjected to a constant magnetic field of magnitude 0.5 Tesla, which is directed as shown. What are the magnitude and direction of the current in the wire needed to remove the tension in the supporting leads? So the information is given in the form of diagram. So you can see the first diagram, that is A. So you can see a wire whose length is 50 cm. It is suspended by means of two leads. Okay, and you can see the cross symbol there in blue color. That cross symbol in blue color, it shows a uniform magnetic field. And since it is cross or into symbol, the direction of magnetic field is into the plane. Into the plane of the book or whatever we are considering now, into that plane, that is what is shown by that into. Okay, so here the direction of that magnetic field is into the plane. Okay, now this is the situation given and you are asked to find, the question is to find the magnitude and direction of the current. You have to find the magnitude and direction of the current needed to remove the tension in the supporting leads. How to remove the tension in the supporting leads? Tension in the supporting leads is removed by equalizing the forces. Here which all forces are coming into action? One is the force on the wire due to this magnetic field, and the other is the gravitational force, that is the weight which is acting in the downward direction. So that you can see from this free body diagram. In this free body diagram, the two forces are shown. Fm, that is the magnetic Lorentz force which is acting in the upward direction, and in the other one is acting in the downward direction. So to equalize the or to neutralize the tension, that means there is no tension. It means that the two forces should be in opposite direction and their magnitude should be same. Then only we will have that condition. Okay, for that the current should flow in which direction? So as it is given in the diagram, as per the given situation, using left hand rule, Fleming's left hand rule, you can determine the direction of current. You keep your fingers as per the given situation. You will get the middle finger to be in which direction, from left to right direction. Do it yourself. So that direction of current is in that direction as it is shown in the free body diagram. So what should be, so that should be the direction of current. Now to find the magnitude, we can equate the magnitudes of Lorentz force and weight. What is the magnitude of Lorentz force? Magnitude of Lorentz force is BIL, because here it is perpendicular. The current and magnetic field are perpendicular to each other. So we have mg equal to ILB, or I is equal to mg by LB. So do the substitution and find the answer yourself. Now this is a problem from textbook. A straight wire of mass 200 gram and length 1.5 meter carries a current of 2 ampere. It is suspended in mid-air by a uniform horizontal magnetic field B. What is the magnitude of magnetic field? So it is suspended in mid-air means what? By a uniform horizontal magnetic field means by the suitable application of magnetic field in proper direction, we are making sure that that wire is under the action of an upward force, and when the upward force and the weight becomes equal, the wire becomes freely suspended in mid-air. Otherwise, why the wire is coming down? It's under the action of this gravitational force, the wire is falling down. So to make sure that it is suspended, the wire should be under the action of an equal upward force. So how can we achieve this? That is by the application of magnetic field. So we can equate, as we did in the previous example, we can equate the gravitational force, that is the weight mg, with the Lorentz force, that is mg equal to ILB, and find B. So we have B is equal to mg by IL, and we get the magnetic field as 0.65 Tesla. Okay, so that's the answer. With that, we conclude today's lesson. Thank you.